Okay, so we're going to go back and we're going to, this is Math 409, problem solving lecture 28, so doing more Putnam problems. So we're going to go back and we're going to revisit the problem from 2003. Let n be a positive integer. How many ways are there to write n as a sum of positive integers where a1 is less than or equal to a2, less than or equal to a3, all the way up to less than or equal to a1 plus 1. So what that means is we can only use two different types of numbers. We can use just ones or ones and twos, or just twos or twos and threes, or just threes, and so on and so on and so on. And so the first thing to do is to gather data. And we did this before. If we have 1, the only way to write that is 1. If we have 2, it's 2 or 1 plus 1. If we have 3, it's 3, 2 plus 1, or 1 plus 1 plus 1. If we have 4, it is 4, 2 plus, I'm sorry, 3 plus 1, 2 plus 2. Oh no, we can't do 3 plus 1. Sorry. So if we have 4, it's 4, it's 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So looking at this, it's natural to conjecture that the number of ways to write n is just n in terms of this decomposition. So we now need to prove this rigorously. How might you prove this? Induction. I mean, it seems to be screaming at you, do this by induction. If we know how many ways there are to do 4, we should be able to find out how many ways there are to do 5. So one possibility is to take what we know from 4 and move it up to 5. The other, of course, is look at all the decompositions from 5 and show that they all collapse down to something from 4, except for one extra one that's added, that's new. Okay. So do you want to try to move up or do you want to try to move down?
Down.
So try to move down. All right. Let's move down. So we have n plus 1. And we look at all of its decompositions. So if I give you the decomposition of n plus 1, now let's move down. What would we get? So we have to subtract 1. We have a smaller number. So what would be the decomposition that this would move down to? N. And nothing else moves down to n. Now, what about the next one? Well, if we have n, it would have to be n and n minus 1. Or it could be, we can't have n and n, right? Because if we had n and n, that would add up to 2n. So we have to figure, so we have some general term. So maybe we have, A, B, B. And what's the relationship between A and B? So B equals A plus 1, or we might just have all A's. And so how do we want to move this down? A, B, B, B.
Pick the first B and turn it to A.
So which is the first B, the one on?
Oh, from the left. Going
the first one from the left. So this would become, A, and then we would have now a new A over here, and then all B's. And in the other one, what would we have?
Turn the A into A minus 1.
Into, yeah. So maybe A minus 1, and then A all the way down to A. Yeah, maybe. So we've got to be careful in terms of, could we have repeats? Could we have two things going to the same thing? So when could we have trouble? Are there any values of A and B that might give us pause?
A is 1.
Yeah, so there's some concern if A equals 1. So if I give you a bunch of 1s and a bunch of 2s, how could I move this down? So one possibility is I could move it down to the same number of 1s, add a 1, and then all 2s. Or what else could I do? Drop the first 1. And then have the same number of 2s as before. So these would be two distinct decompositions. So is there anything else that could go to these numbers, to these decompositions? What else could go to the bottom one? 1, 1, 2, 2.
And like a number with a lot of, well, n plus 2 2s, and then, well, yeah, so.
So what else could go to this?
You would be in the blue sequence, like the one on the right, if that was a 2 also.
Right, but it wouldn't be exactly the same as the sequence, because I can't just make that a 2. What would I have to do as well? If I just make this a 2, I've made the number larger. Take off another 1. So if I take the number that's 1 dot 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 2, and then all the 2's over here, that will also go up to this. And notice that's not the same decomposition as this one over here. It has 1 fewer 1 and 1 more 2. So we actually have some of these decompositions can actually go to two different things. At the very end, when we have the number that's just all 1s, how many things can that go to? It can only go to one thing, right? That has to go to 1 fewer 1. Is there anything else that could have gone to that? What else could have gone to this?
That's not a word.
If this was a 2 and everything else was a 1. So if I have 1 dot 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 2. So we have a bunch of things that are going to two different items. But there's a lot of repeats that are happening. And the final thing of all 1s doesn't go to anything new. So if we go back a slide and we look at what's going on here, the 4 is just going to go to a 3. What's the 2 going to go to? That has to go to 2 plus 1. What's the 2 plus 1 plus 1 going to go to? So this can go to 1 plus 1 plus 1. What else can it go to? 2 plus 1. So that goes to two things. And what does the 1 plus 1 plus 1 plus 1 go to? 1 plus 1 plus 1. So when you look at that, you can see we had 4 items and it goes to 3. So the 2 plus 1 plus 1 goes to two different things. One of them we had already hit, and one of them was new. And that's what you have to go through carefully and say that as we're marching down, until we hit the 2s and 1s, everything's going to something unique. When we finally hit the 2s followed by the 1s, that's the first time we have something that can go to 2 different things. And the first thing it goes to, we had actually already hit from taking one of the 2s and making it a 1. And so it still generates something new. Then the next one can go to 2 different things, and it generates 1 new thing. And then in the end, this last thing doesn't go to anything new. It goes to something already hit. So now I have to now reinitialize. And so that's what you have to write up, very carefully, very clearly. That as we're marching down, we are generating new things throughout until the very end, when we generate 2 things we've already seen, when we generate something we've already seen. And the other ones, when we're generating 2 things, one of them is new, one of them we've already seen. And you just have to write that up really carefully, really clearly. If anybody has another way of doing this problem, that's an easier way to write up, I'd love to see. To me, this is not something I'd be eager to write up carefully. Drawing lots of pictures, sure. Okay. Anything else from any of the problems here? So the other ones we hadn't done is this new operation star, and then 1992, this function f of n is 1 minus n, so it's the only function satisfying these 3. Nobody has a preference, I would choose 92.
I want to see 2001 actually.
Okay. All right, can you do 2001? No. Has anyone tried 2001? All right, so let's do 92 first, because 92 I think is easier, and then see if we can use the ideas from 92 to do 2001. And what movie starts off with 2001 as part of the title? Very good, yes. And who wrote the book? Cultural credit. No. Nope. It was not Asimov. He wrote Rendezvous with Rama, Childhood's End, The 9 Billion Names of God, Arthur C. Clarke. Okay, so for this problem, they're giving you the proposed function. F of n is 1 minus n. What's the first thing you should do? Yeah, check and see if it satisfies the conditions, right? It should, just in case there's a typo or something in the problem, quickly check and see, does it satisfy? Check f of n equals 1 minus n satisfies. It does. I'm just assuming it does. The Putnam should be very heavily checked, but it is possible that there could be a mistake. What would happen if f of n equals 1 minus n does not satisfy the conditions? What'd you do? You would write that down and say it is not. And then if you have time, come back and try to figure out what is the function that satisfies. Okay, so
Sorry,
yes.
Are we supposed to register for the Putnam already, or is it just like you show up?
I think it's now you just show up. Would you have to register? Oh wait, did I email you all a form?
I think so.
Okay. I'm not sure. Send me an email and I will resend it.
Yeah, but it's very.
Yeah, I mean, we always register. It's being recorded now, so I will stop here. So when you're trying to do problems like this, and they give you a couple of conditions and iterations and whatnot, you should always try to figure out good n to try. What is a good n to try? Any thoughts? There are 2 good n's to try. 0. Why is 0 good? Why would n equals 0 be a good thing to try?
Oh, here's one of the.
Yeah, it's one of the conditions. We know f of 0 equals 1. So we now get f of 0 equals 0, or f of 1 equals 0, right? We also know that f of 0 plus 2 equals 0, or f of 2 equals 0. But what is f of 2?
I think it was.
Or did I make a mistake? Oh, no, there's a, I'm sorry, there's a plus 2 inside. Sorry. It's f of 2 plus 2, right? Okay, sorry. So we have f of 2 plus 2 is 0. Why? Why is f of 2 negative 1? We don't know that. Right? We're trying to prove that the only f that works is f of n is 1 minus n. We don't know that yet. But what do we know about f of n? F of n equals n. So what do you do? So when you apply f to f, what do you get back with math? The identity. So from the first point, we know f composed with f is the identity map. What should we do to this equation? Yeah, apply f to it. Right? So when you have problems like this, it all comes down to what's a good place to evaluate, what's a good way to iterate with the knowledge I have. So we apply f, and we find f of 2 plus 2 equals f of 0. So this is just f of 2 plus 2, and what's f of 0? F of 0 is equal to 1. So f of 2 equals negative 1. So things are looking pretty good. Right? We've now shown f of 1 is 0. We've shown f of 2 is negative 1. It's looking a lot like this is the right function. Can you think of what would be a good thing to try now?
Oh, yeah. Do we use we have like different ends and then just go with section or kind of like that?
So what should we do next?
F of like 1 plus 2. Sorry, f of 1 plus 2 plus 2 equals 1.
Okay, so you want to try f of what?
F of 1 plus
1 plus
2.
2? Like this?
Plus 2. Oh, no.
Okay, and where are you getting this?
No, and then plus 1. Oh, sorry, plus 2.
Are you getting this from 2?
Yes.
Okay, well, if you're getting this from 2, why not just apply f to 2? Your 2 is talking about f of something. Oh, well, if I've got f of something, if I just apply f to the left-hand side of 2, what happens to that f on the outside? I'll have f of f. What's f of f? Goes away. So just apply f to the second condition. And now we would just get f of n plus 2 equals n. So f
On the right side.
f of n, thank you. So what can we deduce? So we get f of n plus 2 is f of n minus 2. So we can induct on the evens and the odds. So if you know it for n, you know it for n plus 2. So no, we have to do this for all the values. Okay, so if no for 0, no for 2, 4, 6, ... What about going in the opposite direction? So do you agree that if we now know it for, if we know that f of n is 1 minus n for 0, we now get it for 0 plus 2. And then we would now know it for 2, so now we get it for 4. If we know it for 4, we know it for 6. So we can march up. Can we march backwards? Okay, just do it the other way. So now assume we know it for n plus 2, and now we get it for n. So it can go backwards. So minus 2, minus 4. So does everyone see how we can go in both directions? If I know it for 0, I now know it for 2. Now I know it for 2, so I know it for 4. Now I know it for 4, I know it for 6. Or I can go the other way around. If I know it for 0, so it would be negative 2, I now know it for negative 2. If I know it for negative 2, I would now know it for negative 4. Because I would now take n equals negative 4, and this would give me f of negative 2. So everybody comfortable that we can march upwards and backwards? So if we know it for 0, fine. Now we also need to know it for one odd value, but we know it for 1. So no for 1, so march again. And again, you would want to put in a little bit more detail than this, but it turns out it was actually very good that we calculated that f of 1 is 0. So this turned out to be 2 different inductive chains, because we don't have a relationship between fn and fn plus 1. We have a relation between fn and fn plus 2. So these problems, at least for A1, you should be, okay, that's how. So you have this advantage when you're taking the Putnam. There has to be a nice way of looking at it. There has to be, what's a good choice to take for my input? What's a good way to somehow take the given information and iterate? And so for the most part, there's probably not going to be that many red herrings. So if they give you something, it's probably important. Sometimes they give you things accidentally. We saw some problems where they wrote as like 9 plus 8 plus 7. And when I saw that, I was thinking, oh, maybe you throw away the highest power of 3 you can and look at what's left over. For one of the problems, they listed 4 has 4 decompositions. Well, okay, you haven't told me how many decompositions 1, 2, and 3 have. This is not my first time around. Let me calculate those. Oh, 1 has 1, 2 has 2, 3 has 3, 4 has 4. Okay, interesting. So probably maybe n has n. So gather some information. Sometimes when you have a problem like this, if you don't see what to do, just try putting in a few different values and see if you can find something. There is another value of n that might be natural to take. There might be another value of n that might be natural to take. Yeah, negative 2. If I take n equals negative 2, I would get f of 0, which is 1, and then I would get f of 3. All right, well, what is f of 3? Well, but then if I realize, but f of n is n, so if I have, if I take negative 2, f of 0 is 1, so I have f of 3. If I take f of both sides, I would get f of 3, so I would get 3 equals f of negative 2. So now I would know the value at negative 2. And so maybe we can somehow get chains like that. But it's extremely important that we figure out both f of 0 and f of 1. So we have the even and the odd chain. Okay, any questions on this? All right. So, all right, so let's take and copy this one. So I have no idea how to do this one. I have not looked at these problems that much, so I can try to be, live thought process. All right, so we're giving you some operation star, and we're saying that whenever A and B are in a set S, so is A star B. Anybody know what this property is called? Closure. So it's closed. And they want you to show that A star B star, assume A star B starred with A is always equal to B. They want you to prove that A star B star A is always equal to B. Okay. Have no idea how to do this. What should we do? So we don't know that star is associative. We don't know star is commutative. We just have a relation. What should be the first thing we do? If you have no idea, what should we do? We are told, so we know for all A, B, and S, we know A star B star A equals B. So what might we try to do? This is true for any A and B. What do we know? What can we do?
Start this with A star B on the right.
Oh, okay, so we could start starring things. And so it's a binary operation. And so when we start with something, how does that combine things?
Know that A star B is some other number set.
So we could say A star B is some number C sub AB. And what did we do when we had the previous problem with the F's? What was the very first thing we did? It may not be the right thing to do here, but it's something to try. Set A equals B, do some special cases. So special cases. If A equals B, we get A star A equals A, and we know B star B star B equals B. Okay. So that's one thing that we can immediately conclude.
That A cross or A star A is it could be an identity.
We don't know what it is. We don't know anything about it. We just know. Now, we could take B to be A star B or B star A in the identity. I don't know if that's going to be useful, but if this is true for any B, here's two things I could try. And if I do that, I would get A star, and then B, if I take as A star B, and now the parentheses really matter, star A is equal to A star B. And I could take it to be B star A, so I would get A star B star A is B star A. So does any of this look useful?
Oh, for the right one, could we do an A on the left side?
For the right one?
Like A on the right.
Well, so notice here, this is actually in some sense what we want. We want that to equal. I gotta try to figure out how to stop the. There must be some setting that's somehow been changed in terms of how long the screen lasts. So I'll try to figure out what that is. I'm pretty sure it was just a coincidence that I just happened to hit the board at that moment. So notice that this is exactly what we want. We want that to equal B. And if if things were invertible somehow, we'd be in great shape. So we do know that if we star this with A, Jesus. It's like 2 seconds. All right. I'm not going to touch the screen. I'm going to just keep having my finger tapping this. All right. So we have A star B star A equals B. We could, of course, also switch. And if we switch the roles of A and B, we would get B star A star B equals A. Right? Just switching the roles of A and B. Right now, what I'm doing is I'm just trying to throw down as many facts as I can. I don't know how to solve this problem. So I'm hoping that eventually I will have almost mathematical, vomit all over the place here. And then I will circle the parts that actually matter and then connect them in a logical way. And so just trying to think, does any of this help me? And so, if I take this and I were to star it with A star B star A, I know that would just be B. And so I could star this with A. But the question is, how do, we need some way of combining things. And so it's a binary operation. And so if I star the right-hand side or the left-hand side, I would then have this whole thing, which is just something in S starred with it. And I don't know how I would connect that with something individually. If we assumed that things were associative, would this problem be easy or hard? Easy, because if it was associative, then A star B star A, I can just do A star B first, and A star B star A we know is B from that. So it's trivial if associative. So trivial if associative, A star B star A becomes A star B star A becomes B, and done. So must assume not necessarily associative. Right? That's not going to be the Putnam problem, is to just regroup. So we have a more general set. We can't assume that it's associative. So the question is, if we can't assume it's associative, we can't just change the groupings. The groupings matter. And so I think what we need to do is we need to look at what we have here and try to plug that into the relationship. What is our relationship? Our relationship is X star Y star X equals Y. So if we wanted to, maybe this whole thing here is X, and that's Y, and then we could start by X again. Or maybe over here, A star B star A is X. I'm trying to figure out, maybe something like that is how we want to do it, is to have X somehow related to these longer, more involved expressions. So any thoughts? Did somebody just see something cut across the screen?
On the fly.
Okay, it was a fly, okay. Any thoughts as to how we might want to try to do things? So we can try to, we have two objects here, we need three. So we've got to figure out what do we want to try to do for X and Y.
X equals BA and Y equals B.
So what do you want to try?
X equals BA,
Try X equals BA
yes, and Y equals B.
and Y equals B. Okay, now this would give us B star A star B star B star A equals Y, which is B. And do we have that? So if we look at what we have over here, we have the B star A. We could start this with B star A star B, but we don't know how to combine that.
Oh, yeah, but you can start the left bracket kind of direct, like
Left side.
we do BA, B equals A.
Seconds.
Oh, well, so given that BA, B equals A.
We're given A star B star A equals B.
Yeah, but
Left
star
simplified.
A star B.
So this simplifies.
Oh, sorry, it's the green expression down there. On the left side.
This?
Side's down to A.
Okay, that's A from
First
the first condition. Okay, so this then becomes, so now we know that this is just A star B star A equals B. And that's what we wanted. Okay. So I'm not even sure if we use the blue stuff.
B star A star B.
You switch A and B.
You switch A and B. So we know A star B star A equals B. Now that A equal B and B equal A, and then you get that as well. So we just switch using which is A and which is B. Did we actually use the blue stuff? No, I think we just took the relationship X star Y star X equals Y and just tried to think what are good things to substitute in. And if you think about it, the natural things to substitute are in A, B, A star B, B star A star A, and there's one other one, B star B. So basically just take the identity and shove all the candidates. So never used blue, try X and Y from A, B, A star B, B star A star A, B star B. How many possibilities are there for X? Let's say 6. How many possibilities for Y? 6 gives you 36 things to try. 36 is significantly less than positive infinity, right? You've got 3 hours, 36 things to try, not so bad. Okay, so fortunately you gave really good ones. It's just very similar. I've got my identities. What are good things to substitute? And one of the key things is just when I have this, look at all the different ways I can write it, because the order of A and B matters. So as soon as I have this relationship, it's true for any A and B. If I'm looking at two special elements, let me write it in both different ways. All right, so this is a good place to stop.
Well, let's go over this.